Hello everyone, this is Sean Yu, your 5111TA, and today we'll be talking about transition metals in preparation for your final exam. So here are the list of things that you need to know about transition metals. We'll be talking about these in detail. So first of all, we need to know how to calculate the d electrons. So the number of d electrons can easily be calculated by subtracting oxidation state from the group number of the transition metal. So I listed some examples of calculating d electrons. So let's just go over calculating the electron of iron 2+. So iron 2+ have oxidation state of 2 and is in group 8. So the d electron count should be 8 minus 2, so 60 electrons. Now, you also need to know the shape of the d orbitals for the transition metals. So notice that for dyz, dxy, and dxz, you have lobes lying in between the axes, while for dz squared and dx squared minus y squared, you have lobes lying along the axis. Now, let's talk about crystal field splitting diagram. A key concept in crystal field splitting diagram is that you have repulsion between the d electrons and the ligand. So the d orbitals that have the least repulsion with the ligand has the most stable energy. Okay, so now you have crystal field diagram for octahedral, tetrahedral, and the square planar system. Notice that for octahedral you have dz squared and dx squared minus y squared at a higher energy level than the 3d orbitals lying in between the axes, and the pattern is flipped for the tetrahedral system. And you have a little bit of complication in the square planar system. Now, how do you understand this complexity that arises in the square planar field? Well, an easy way to think about it is, so for square planar field, imagine you're starting with the octahedral field. And imagine that you are slowly increasing the distance of the ligands lying along the z-axis. As a result of increasing the distance, you have the stabilization of the dz squared orbital, because those dz squared have load lying along the z-axis. So you have dz squared becoming lower in energy compared to dx squared minus y squared. The same trend goes for dyz and dxz. Since these two orbitals have some component of their orbital lying toward the z-axis, you have the stabilization compared to the dxy orbital. Now, you also need to know how to calculate the crystal field stabilization energy. So as an illustration, let's talk about manganese CO6. So we know that manganese is 3+, so you have 4d electrons, and you know that CO is a strong field ligand. So you place the 4 electrons on the lowest energy orbital, which is the T2G set here. And for each electron placed on T2G set, you have a net stabilization of 2/5 of delta 0. So the crystal field stabilization energy should be 4 times negative 2/5 delta 0, thus you get minus 8/5 of delta 0. Now, how do you know a ligand is a strong field or a weak field? Well, that's why we have the spectrochemical series listed below. So all you have to memorize is basically the fact that CO and Cn- is a strong field ligand, and water and ammonia is a medium strength ligand, and halogens are weak field ligand. So you will learn about these trends in detail in more advanced chemistry classes, but for now just memorize a few examples of strong field and weak field ligands. Now let's move on to our main business. So here are the questions from the actual final exam in the past. So first, calculate the electron count for iron 2. We just discussed that iron 2 has 60 electrons. Now, draw the octahedral crystal field splitting diagram for iron 2 for weak and strong octahedral field. Well, for weak field, you should maximize the number of parallel spins. So you place the electrons on the EG set, and for strong field, you try to put as many electrons on the lowest energy orbital, which is the T2G set. How do you calculate CFSE for high spin iron 2? Well, you go back to the diagram, and for each electron placed on the T2G set, you have -2/5 of delta 0, and for each electron in the EG set, you have 3/5 delta 0 destabilization. So you sum it up and get crystal field stabilizing energy of -2/5 delta. How do you calculate CFSE for low spin? Well, in that case, you place all your electrons in T2G set. Thus, you have CFSE of -12/5 delta 0. Now, would iron hexacyanate be high spin or low spin? I just discussed that cyanate is a strong field ligand, thus you have a low spin system for iron hexacyanate. Now, calculate the octahedral crystal field splitting energy. Well, we know that delta E is always equal to Hc over lambda, so you plug in all the numbers and convert it into kilojoule per mole, and you get 392 kilojoule of crystal field splitting energy. Now, this is the energy difference between Eg and the T2G orbital set. Now, drawing the orbitals, that should be easy. So for a molecule that have ligands placed along the z-axis, you can predict, according to the crystal field theory, that the orbitals lying along or toward the z-axis will have net destabilization. So you'll have dz squared higher in energy compared to dyz. Now the final question. You're asked to draw a crystal field splitting diagram for octahedral crystal field and tetrahedral crystal field. So the net d electron count is 8, and for octahedral system you have 6 electrons in T2G set and 2 electrons on the EG set. So this is the same regardless of whether the ligand is strong field or weak field. And for tetrahedral diagram, you know that Eg level is lower in energy, so you have a crystal field splitting diagram as shown here. And for both cases, you can explain the presence of paramagnetic species. So as a side note, when you draw a tetrahedral diagram, notice that you always have a high spin system, regardless of the ligand. So when you have a tetrahedral ligand field, you don't worry whether a ligand is high spin or low spin ligand. You always have a high spin system. Okay, that was the end of the review session, and everyone, good luck with the final exam. This was Sean Yu.